So let's bring out our next swashbuckler. Damir here is coming to us from San Francisco, is that right? Working at Netflix as a senior software developer. And he is into punk, so I'm hoping he'll rock the boat today. And we weren't sure, but we saw in a tweet of yours, Damir, that you either found or gave away a box of programming books.
I found it on the street in San Francisco.
Yeah, so that's something that happens in San Francisco,
Yeah,
apparently.
only there. Yep.
So, well, without further ado, take it away, Damir.
Thank you. Okay, great. Hi, EuRuKo. Glad to see all of you here and hope you're having a good time. As said, my name is Damir Svrtan, and I work in the studio engineering organization inside of Netflix. Now, Netflix is often referred to as the pioneer of the microservice movement, and I want to talk to you about my practical experience after being surrounded by microservices and some of the patterns that our team uses to tackle distributed data. Most of us from Europe, so I'm actually from Croatia, know Netflix as a streaming service, but Netflix actually existed for 10 years before getting into streaming as a business that shipped DVDs to your home in red envelopes. You would open up the envelope, take the DVD in, watch the movies however many times you want, return it whenever, and there were no late fees. A fun fact, I thought that this business stopped working, but it's actually used by more than 2.5 million people in the United States. So the DVD rental business was the first phase of Netflix. The second one, as I've mentioned, was the streaming service, which changed how people watch content. It was a risky move back then. Streaming technologies were not good in 2007, but eventually Netflix provided a way for people to watch great content without being disrupted by endless commercials. I'm not sure if you've ever watched cable TV in the US, but the amount of commercials is actually ridiculous. Some channels actually feature more than 15 minutes of commercials within 1 hour of programming. It's basically unbearable to watch. So in 2013, another big shift happened at Netflix, and that was producing original content. What started in the early days with House of Cards and continued with Orange is the New Black and Stranger Things, now Netflix produces hundreds and hundreds of original shows and movies each year, which is way more than most major film studios combined. Now, was that a big shift? It surely was. All of a sudden, Netflix came from being just purely a technology company where everything is fully automated and performs efficiently into the entertainment business. Now, the movie-making business is a 100-year-old industry, and in many ways, unfortunately, it hasn't changed a lot since it started. Most of the work is still done on paper, and it requires a lot of manual labor. So, do you remember these? Fax machines. I personally don't have an idea how to use one of these, but basically every single movie production uses fax machines. They're used constantly on sets to distribute massive amounts of paperwork. Just to give you a sense what massive is, there are instances of movie productions that manage to print out more than 50,000 pages within the first week of shooting. Basically, at the scale that Netflix is producing content, these traditional means do not work well. So the problem space and the number of domains for movie productions and film studios is huge, from deciding which scripts are going to be produced, to deciding what content will be acquired, searching and discovering talent, managing contracts and paying actors, finding shooting locations, title localization, subtitles, dubbing, marketing. It's basically absolutely endless. So how does Netflix tackle these problems? Netflix tackles this by using technology and creating apps that cover key part of every production. Netflix is creating a first fully digital studio to help automate the boilerplate and boring parts that usually creatives do not want to do. We're talking about a suite of more than 50 applications that help with covering the previously mentioned areas. Now, Netflix actually started tackling the studio space with a monolith, with a Rails application. It allowed for rapid development and quick changes while the knowledge of the space was non-existent. There are many other apps currently at Netflix and Netflix Studios, but this is still the biggest and the most used app there is. It is pretty big, and at one point it had more than 30 developers working on it and well over 300 database tables. Now, a lot of these areas started getting specialized apps, and we basically started decomposing the Rails monolith and migrating data into various specialized apps or microservices. The decision was not geared by any kind of performance issue, but with setting boundaries around all of these different areas and domains. Now, I've joined Netflix about a year ago, and as I've joined, our team started working on a new app that crosses multiple domains of the business. We decided to build this app with Ruby and Rails. We had the expertise with Ruby and Rails. It supports agile development. It brings up team velocity. Time to market is minimal, and the amount of gems is unbelievable. We don't have to build already built stuff. Now, one of the key elements that describes Rails is its pragmatic use of the active record pattern. The active record pattern mixes a lot of things into one class: the main objects, business rules, validations, persistence, and that is great for rapid development. However, that's how we end up with models that are tightly coupled to the database, and decoupling those is a pain. Now, why am I talking about decoupling? Well, what makes working in the Netflix Studio world special is that you start dealing with a lot of distributed data. If you need to work on a project that cuts through multiple domains, you start dealing with various different data sources. It's a polyglot environment, and these are some of the examples of technologies from where we can get data. Our users and their permissions might be behind a REST API, while our movie information might be behind a gRPC endpoint, and so on. And a lot of applications actually consume data from these services. So one thing we need to tweak in regards to Rails is the persistence layer. We have a key thing to keep in mind also when building a new app, and that is the data that lives in our database today might live in a service tomorrow, and its whole behavior might live in a specialized app. So some of the data we have in our local database today might have a way broader use case, just the domain might explode, and so the source of truth of that data might actually transfer, and we have to deal with it differently. It might be behind some gRPC or a REST API or something like that, and we don't want to rely on the protocol. So basically what we need is architecture that clearly separates the business logic from any kind of implementation details and protocols. And with all of that in mind, we realized that the perfect architecture for the problems we are solving is the hexagonal architecture. The idea behind it is to put inputs and outputs at the edges of our design. Inputs would be requests hitting the app server or any kind of invocation you have from the Rails console, and that would be the green part, while the outputs would be the yellow part, and that's data flowing into the persistence layer. It might be a SQL database, a NoSQL database, some kind of Elasticsearch, a notification system, or whatever. Basically, in doing so, we isolate the core logic, the central logic that we have here, from any kind of outside concerns. Having inputs and outputs at the edges means we can swap their adapters without changing the core code at all. Now, let's go through a couple of core concepts that we have here, and these are by no means any kind of new and revolutionary concepts, as most of them you might have heard, obviously, from hexagonal architecture or Uncle Bob's clean architecture. Now, at the heart of our domain, we have our entities. An entity in our case at Netflix Studios is a movie, a production, a shooting location, an employee, and so on. And entities by themselves do not know where they're stored. This is unlike what Active Record does. Another core concept that we have are the repositories. They are our interfaces to getting entities as well as creating and changing them. Methods defined on them usually return a single entity or a list of entities, and they keep a list of methods that we use to communicate with data sources. Now, what would be our data sources? They're basically our adapters to different storage implementations. A data source might be an adapter to a SQL database, to Elasticsearch, to a REST API, or even something more simpler, just a JSON file or a CSV file or a Ruby hash. And that's usually where any kind of saucy implementation of fetching and pushing data is kept. And then at last, we have our interactors. There are classes that orchestrate how a certain domain action is performed. They're very similar to what developers usually call use case objects or service objects. Basically, they're classes that are very explicit about what they're doing, and they implement complex business rules and validation logic specific to that domain action. So, talk is cheap. Let's see how we implement these concepts in our app and how we generally design our domain with them. Let's start with entities. An example of an entity in the Netflix Studio domain would be a production. such as Black Mirror Season 2, or a season of Stranger Things, or a movie production such as The Bird Box. Now, each of them have an ID, a title, and a logline. To represent them, we use the dry-struct gem from the dry-RB family of gems. Dry-struct enables us to describe entities by listing their attributes along with their types and which of them are required and which of them are optional. As said, they don't have any kind of knowledge of the persistence layer. Those are outside concerns. We need to be able to model our domain without the data source implementation details. Now, for repositories, we use a custom thin DSL layer to describe them. We describe which entity they work with and what is their default data source. So in this example, a production repository will work with the production entity class and will, by default, work with a movie production class, which is usually just an active record model. And as said, they keep a list of methods that we use to communicate with data sources. So you can see it's basically delegating a lot of those to the data source, and we wrap those data source results into the entity classes or instances of the entity class. You can see that we inject the data sources into them. We want to be able to swap those data sources whenever we need. The only thing those data sources need to is conform to the same interface. Now, what would be our implementation of a data source? If we're talking directly to our SQL database, our data source will be just an active record model. That's where any kind of SQL logic, such as selects, groupings, or aggregate functions will be. And those implementation details are kept directly in the data sources, as they should not leak their implementation details further into the business logic. If we're talking to some REST endpoint, like if we were getting our movie productions from an API, we'll need to create a class that will fetch data using some kind of a REST client. And you can see that both of these classes have the same interface. This makes our repositories independent of our data storage system. As we can have a default one and easily use a different one if we need to swap a data source at a given moment. Changing a data source in this way does not whatsoever impact our business logic, which is great. And another thing we can do with this is we can perform it with one-line changes, so it's also very easy to roll back in situations if we got something wrong. And finally, let's talk about how we implement interactors. For building interactors, we use the Interactor gem. The Interactor gem is great as it provides a uniform way to state whether an action is a success or a failure. Now, we built a small DSL on top of it that enables us to define what the dependencies are. So for the main action of onboarding a production, we will pass in what the production ID and what the content vertical ID, whether it's a movie or a show, and then we will instantiate and call the call method on it, which will validate the inputs, check if it's okay to onboard a production, and then cover various other edge cases, and then notify others that a production has been onboarded. Design like this makes our business logic totally decoupled from the persistence layer and follow the single responsibility principle. If you look closely, you can see that actually we pass the repository as the default parameter. Why? Well, we actually leverage dependency injection to properly unit test our interactors, which I will talk about later on. Now, one thing I want to mention, Rails, this is not the Rails way of doing things, definitely. Although Rails does not aim at separating business logic and persistence like this, there are frameworks that build, which you can build apps using clean architecture fashion. So if you're interested in that, check out the Hanami framework. Hanami is a great framework that follows these principles, and basically all the terminology that I've just mentioned is implemented in the Hanami framework. The reason why we didn't use it back then is because we wanted to leverage the large ecosystem around Active Record. Gems just as like Counterculture or Access List and a bunch of others that enabled us to move fast and ship features on a regular basis. So that's it about the business logic and the core of it. Let's talk about implementing data sources. We have touched the data sources part a little bit, but let's talk more about implementing data sources that actually depend on external services. So as we consume data from different APIs, we need to have a lot of API clients. And there are two main approaches. We could write clients by hand and package them in gems. And in a lot of scenarios that makes sense, just for us it doesn't. it takes a lot of time to write them, they are error prone, they easily get out of date, and you have to always add new features by hand. Generally, the maintenance burden is too heavy, and it simply does not scale for us. What we opt in is for auto-generated API clients. It's basically any API that we work with has to be able to provide a way to easily interact with, either by following a specification or having documentation from which we can generate a client. So REST APIs usually have Swagger documentation on Netflix. From that, we can actually use the Swagger code generator to generate a client in Ruby. And we usually package those clients in gems and publish them to a local repository. With gRPC, we can also generate clients easy. And then with APIs that follow the JSON API specification, which prescribes a uniform way to expose resources and receive requests, there are gems that enable you to easily communicate with them without spending days and days of actually writing any kind of API clients. Now, if you go down this path of communicating with microservices, one thing you'll have to deal with is errors, and that is a big shift. When your only data source is the database, rarely anyone adds extra code for cases where when there's a database outage or something like that, as those generally rarely happen. But if one thing is sure, it's that the network is unreliable. This kind of happy path thinking that we usually take with databases does not work well in a microservices environment. Microservices will definitely fail, and there will be outages, even at Netflix. Now, one thing we need to be prepared for is graceful failure. What is the experience if a downstream service fails or has a total outage? We need to be sure that a single outage does not take the whole application down, and we need to be sure that we at least are able to serve some partial data and give clear error messages to our users. An essential part of this is being properly able to troubleshoot errors when communicating with downstream services. If some kind of a 400 or a 500 occurs on a downstream service and you're not sure why that happened, without proper logging, troubleshooting is basically a nightmare. Now, another extremely important aspect is measuring, as without that you won't be able to discover what your pain points are. A good way to solve a lot of these problems is having metrics in place, even just simple ones as what is the failure to success ratio on this service, or what are the downstream service response times. Of course, we need to also have some kind of error reporting system, just as most vanilla Rails apps do, such as Sentry, Bugsnag, or something similar. One thing that we need to be cautious is that we don't overload ourselves with unactionable errors. So we should only report errors that are actually actionable. If a downstream service, let's say, responds with a 400 some kind of validation error, we don't want to be alerted by that. But there's not that much that we can do actually there. And the reason why they must be actionable is because errors otherwise just bring alarm fatigue. How many of you have heard of the phrase alarm fatigue? Okay, so if you enter an emergency room or hospital or something like that, probably the first thing you'll hear is a bunch of alarms going off constantly from various different monitoring systems that monitor vital signs on patients, such as the heart rate, the pulse, the oxygen, and so on. As a lot of these alarms are actually unnecessary, medical staff just starts to ignore them. And this was actually a huge problem in the US because between 2005 and 2008, there were more than 550 deaths that were just due to alarm fatigue. Now, our team at the beginning used to report every single thing, even if it was not actionable. As time passed by, we removed a lot of those error reports and we set up threshold alerts on our metric systems to notify us when a larger amount of calls start failing. An example of that would be if 20% of these calls start failing, alert our team. At that point, maybe we're not integrating well anymore, or maybe there's probably some action that we can do to make it better. Now, at this point, a lot of you might be wondering why we'd go straight to the data source instead of like syncing data or something like that. And a question you might be asking is whether this actually scales. Isn't it slow to make additional network calls to other services? Well, before I answer that, let's talk about what would be some of the alternatives. we could, of course, keep copies of that data closer to us in some kind of a database. We could listen to events whenever this data changes at the source of truth and refresh our copies. So basically, we could leverage eventual consistency, as it is definitely the way to go to actually reach true scalability. But at the same time, it's a solid amount of work. There's always the question of trading consistency for availability, and in most cases, availability actually wins. In the case for, let's say, Amazon's or Apple's shopping cart, availability is the absolute winner. People must always be able to shop. If Amazon or Apple sell an item that is no longer in stock, there's really not that much of a problem. They'll just issue a refund or give some coupons, and that's it. Everyone will be happy. But we're also in a very different position. Amazon has huge volume of data, enormous traffic, while our app in the Netflix Studio environment at most has a couple of thousand users. And at the same time, those users actually make big decisions based on the data that we provide, so it actually better be right. We cannot afford the data to be inconsistent. Now, in Netflix Studio, and of course the whole Netflix, services must be reliable, highly available, and respond in a timely manner. If we encounter a service that is slow, team that operates that service will get feedback to optimize it. And we rely a lot on our services being available, and so far the ride has been great. If there is a possibility for us to avoid synchronizing data in our app, that is actually the preferred way to go. Don't get me wrong, a lot of apps at the Netflix Studio work on the eventual consistency model, but they also have a much more specialized use case, so they don't have such a huge variety of data as we have in our app. But what if this actually becomes slow in the future? If in the future we start to deal with huge amounts of data, or we need to additionally decorate some of the data sources or some of the entities that we rely on from external data sources, we'll probably decide to keep decorated copies of that data closer to us. But that's another great reason why this architecture is awesome. It enables us to actually delay decisions. We're not only in a great position when it comes to swapping data sources from, let's say we consume data from a REST API today, but let's transfer to GraphQL or something similar, but also to delay some of the decisions whether we want to actually store data internally or not, and how we want to do it. There's a thing that's called a project paradox, and that is that we actually make the biggest decisions on a project when knowledge is at its absolute lowest. Just think about it. When we start off a project, we decide what language we're going to use, what framework we're going to use, what's the database going to be, what kind of a database, what are we going to use for search, for pub/sub mechanism, and so on. And at the same time, we really don't know much. But as time goes by, the knowledge of the domain gets bigger, and we know where the project is going towards. But the scope of the decisions that we can actually make is lower and lower because we have constraints from the previous decisions that we made at the beginning of the project. So Uncle Bob once said, the purpose of good architecture is to delay decisions. Why? Because when we delay a decision, we have more information when it comes time to make it. So we currently store some of the data in Postgres. But if tomorrow, for whatever reason, we need to switch to some of the alternatives, because we have set up the architecture this way, it is very easy to delay all of those decisions. And we can easily opt in for a polyglot approach where we take multiple of these various kinds of databases or approaches and just use them when it fits our needs. So I want to talk shortly about our testing strategy. We firmly believe that the test suite must be reliable and fast. It's not a nice to have, it's a must. No one wants to run their specs only on the CI server. Stories of developers running their 30-minute spec suite in parallel on 8 cores just doesn't sound efficient. We want to have super fast tests so we have good development velocity. So how does usually Rails testing look like? Well, usually a pattern to test Rails apps is basically just hitting the database a lot. Not, of course, every codebase does it like that, but most apps that I've seen actually constantly hit the database. Now, when testing business logic, do you really want your business logic to be dependent on what the data source implementation is, because we surely don't want to, so we test our business logic independently. We leverage dependency injection to easily test our interactors, where most of our business logic resides. With dependency injection, we can leverage verified doubles and mocks to decouple our core code from the persistence layer. So, as an example of testing that previous interactor that I showed you, we can easily test it. For a production ID and the vertical ID that we're passing in, we can just generate something random. It's not actually stored anywhere. And then when calling the interactor, we can actually inject a mock repository to properly unit test our logic. In a failing scenario, we can inject a mock that returns an existing production, which should respond in a failure in our test case. And with that, we can continue on iterating on more difficult edge cases and other success scenarios. So most of our business logic is tested through unit tests, but we of course have integration specs. Our integration specs are written at two different layers. The first layer of integration specs works on the data source layer, where we check whether we're integrating properly with other services. The second layer we test are basically end-to-end specs, where we basically go through the input, go through the core logic, go to the persistence layer, and get back. And of course, those integration tests are cached with VCR. And we usually build them, in most cases, in a way that they cover one happy path, one sad path, while unit tests cover the rest. What this produces is a fast and reliable spec suite. These are some of the numbers that we have currently. However, we think we can do better. It is generally lovely to work with a test suite that can easily be run on any development machine, and our development team can work without disrupting their work on their daily features. So, in conclusion, hexagonal architecture really proved to be a great way of approaching problems for us. It generally forces us to think in terms of the coupling layers, which is just what we needed. And if you take one thing from this presentation, please let it be delaying decisions. Making most of the decisions at the beginning of a project does not make a lot of sense. The decisions we made so far have been great for us and have enabled us to move fast. But the best part of this architecture is that it keeps us flexible for future requirements to come. Thank you all for listening. Hope you all got a general idea of this topic. This only scratches the surface, so if you want to talk more about it, feel free to stop me in the hallway or at the GitHub booth at any time. Thank you.
Well, thank you.
Thank you. Thank you.
We have a present for you as well. Thank you very much.
Thank you.